Okay, I'm going to do a quick review on the transformations. I'm using square root of x as our parent function here because it's kind of the easiest one to see things happening to. So f of x is our function notation, is equal to square root of x, and what that basically looks like is I start at 0, 0, I go up 1 and over 1, that's 1 point, from there I go up 3 and over 1, that's another point, and so that's what our parent function looks like. So everything that I do from that is going to be a variation of this if it's got a square root in it. So the next question is, typically we can multiply something out front, we can divide inside, we can add or subtract something onto the x, or we can add something on the outside. This changes the y value up and down, this multiplies the y value, this stretches the x value out, and this changes the x coordinate, but kind of in reverse of what we think. So, and if we were going to do that inside the square root, these are the kind of transformations we might see. Probably don't see all of them at once. So a solid example in this very quick review is if I had some function g of x, which was twice the original parent function, which we're, once again, it's our parent function, subtract 1 and then add 3, which I can write this way or I can write this way. Those are equivalent ways to write the same thing because they're all referring back to the square root function. The 1 changes my x value and is backwards of what we think. So it's my endpoint up here is going to go actually to the right 1, but then it's also going up 3. So my endpoint, which would normally be there, is now going to start right here. So this whole thing is shifted up. So if there wasn't any kind of dilation going on here, I would just draw it over 1 up 1, over 3 up 1, and be done. But there is also a dilation. The 2 out there is stretching it out in the y direction. So instead of going, over 1 up 1, we're going to go over 1 and up 2. Instead of going over 3 and up 1, we're going to go over 3 and up 2. And so this is now that same shape, but kind of stretched out in the y direction. Okay, so that's a very quick review. I didn't do everything. A couple of reminders. When the b underneath stretches it out in the horizontal direction. So if that 2 had been underneath there, it would have been over 2 and up 1, and then over 6 and up 1, stretching it out. If it's a negative on the multiplier out front, that flips it upside down, or a vertical reflection. And if there's a negative underneath, or this whole thing in parentheses with a negative underneath the radical sign, kind of inside the function, that's going to be a horizontal reflection. So that thing would be flipped side to side if we had a negative underneath there. Okay, that was review. Here's the new stuff. Our parent function. Let me adjust my camera here. Oops, shoot. Technical difficulties. Okay, our parent function here is 1 over x, which I'm going to call h of x for all my future ones for this particular video. What that normally looks like is I have got a center at 0, 0, so there's my center. And my very first point is going to be over 1 and up 1. And this you just have to kind of verify because you've worked with the sum. But this is basically what the shape is. My vertex is there. This is called my vertex when I'm talking parent function. And this is going to get closer and closer to that, what is going to be my asymptote, which I'll talk about in a minute. And this is going to go more this way. So that's what that looks like on that side. But this thing has a symmetrical part in the other quadrant. So from the center, down 1 and backwards 1, there's my vertex. It's going to get closer and closer, and then down here is going to get closer and closer. And what this is approaching, this center, is the intersection of what we call our asymptotes. So we've got 1 here that is y equals 0, and we have a second one here that is x equals 0. And what an asymptote is a line that a curve approaches but never reaches. So these get very close, but they don't reach. So the important point is that vertex point, if it's not dilated, this is the parent function, so it's not dilated, it's always 1 over and 1 up from the center, and 1 down and 1 back from the center. That's the parent shape. So now we're going to apply our transformations. So a transformation that I might apply might look like this. So this is kind of what we did before. This is adding 2 on the inside of the function, which shifts our x, and subtracting on the outside of our function, which shifts our y. So these are 2 different ways to write the same thing based on our parent function. And so once again, everything's related to the center. So that's really important. So my center is normally at 0, 0. It's going to move down 1 and left 2. Down 1 and left 2, because the x is backwards. So that's my new center. So I have new asymptotes there, which I'm going to sketch in. So I got an asymptote of y equals -1 and x equals 2. Now normally, if this is not dilated, over 1 and up 1 would be my point, and it's not dilated. So that is going to be my point, and then I'm just going to kind of sketch in getting closer and closer to that asymptote, and kind of curving and getting closer and closer to that asymptote. And same thing, I've got this reflective piece down here. So down 1 over 1 is my vertex, back towards the asymptote. So that's just a translation. There's no dilation or reflection going on there. All right, got one more example, and then we'll kind of reverse the process here. Okay, this right here, I'm doing 2 over x, which can be written two different ways. This can actually be either thought of as a horizontal dilation, because this is actually equivalent. If I do 1 over x over 2, it actually becomes 2 over x. You can see that. So that's why this right here and this right here are equivalent. So this both looks like a horizontal stretch and a vertical stretch. Notice I'm not translating it all. So my center is still here. Normally my point would be over 1 and up 1. But because I've done what looks like a vertical translation, that's going to be, instead of up 1, it's going to be up 2. So that's where my vertex used to be, right there, that dot that I probably shouldn't have drawn. And then also it's like a horizontal translation. So instead of over 1 and up 1, it's over 1 and up 2. And this right here is my new curve. So it's still approaching my asymptotes there, which I did not draw in. Looks like that. These here at Ballard we call reference points. You could call them friendly points. But basically it's where your vertex has moved to. Your original parent vertex has now dilated outward by 2. And then, of course, I've got my symmetrical piece down here. All right? So that's a basic dilation without any kind of translation. And then, of course, I could combine these. And I could do some other things too, but we're going to reverse the process now and give you one last hard one. So the question is, if I give you this one, what is the equation? So this is working that same process backwards. So first of all, I probably need to figure out where my center and my asymptotes are. So it looks like I've got a line here that these are approaching. So that's y equals 2. Doesn't look like it's translated at all from the middle. So that's still x equals 0. So for my basic equation, it's going to be y equals, the x hasn't moved at all, so just over x. But then I've moved it up 2, so plus 2. And then the question is, have I dilated it or reflected it at all? So that's probably the first thing you should notice, is normally these things are here and here. So this is a reflection, so we know there's a negative in there. And then finally, normally our point, if it was a reflection, would be right here. That would be our normal vertex point. That's obviously moved, so there is a dilation. And instead of going down 1, I'm going down 1, 2, 3. Or instead of going over 1, I'm going out 1, 2, 3. So this is a dilation of 3. So that's what that would look like. And then my last one is, occasionally you will be giving a weird problem that looks like this. And you may even be given specific instructions to use long division to rewrite in a more familiar form. So long division just looks like this. X plus 1 is dividing 3x plus 2. I need to think, what do I multiply the x by to get 3x? Because I'm trying to subtract to make that go away. So times 3. 3 times x is 3x, but then I've got to distribute the 3 to the 1 as well. That's plus 3. I'm going to subtract all that. 3x minus 3x is 0. 2 minus 3 is -1. So the answer here is 3. And then the question is, do I just write remainder -1? And we don't. We have to remember kind of a trick. If I did 2 into 9, I'd be like, well, that's 4. It's 8 minus 1, and it's 1. So I could say 2 remainder 1, or I could also say, I'm sorry, not 2. I could say 4 remainder 1, or I could also say 4 and 1 half, because I got the 1 and the 2, and so 4 plus another 1 half is actually what 2 times 4 and a half will give me 9. So we're going to do that same trick here. We're going to say, oh, I've got a remainder here, but I want to write it in an interesting way. So I'm going to say, okay, plus -1 divided by my x plus 1. Now this looks very familiar. Sorry, that is supposed to be a -1 there. This is shifted up 3. It's shifted, I got to think about this, left 1, and this just shows a reflection but no dilation. Okay, so I could draw that out fairly easily. That's plenty. Ciao.